All right. So, first of all, any question about the homework due tonight? Yes. You don't have to make it work in Google Colab. But if you don't make it work in Google Colab and don't run it, then the cell states won't be what you might expect it to be. In that case, it's okay. You just have to supply an input file and an output file. So I can see what the input looks like, what the output looks like. And call them input and output. So there's no confusion. All right, no other questions? Well, let's talk about next week's homework, starting tonight. I should make this a lot bigger, and of course you can read it on your own, but it's very similar to what you just did. Except instead of a dumb predictor, you're actually going to do a predictor this time. Now, there were some questions out there. I got one question about how do you handle, what is, recall and precision and accuracy, what do those mean when you're trying to predict a number? Like inches of rain that fell, for instance. Well, this is a good time to talk about these things. I actually was hoping for a little bit of confusion like this because it brings up questions in a way that you remember later. And the first dumb predictor, really what it's meant to do is to predict a class. So there's two kinds of things in general. I mean, a lot of times I'm going to split up the world into two kinds of things. This is one of those times. Regression and classification. Does anyone know the difference? Classification, oh, you do? Go ahead.
So classification is more like bunching things into categories a bit more, and regression is kind of like you have a line that you made a prediction upon, and so like if you give it like a random X value along that same line that should be your prediction. That's what it. So it gives you a number.
Yeah, exactly. So if the black box that you're building outputs a class, like you could think of it numbers like class 1, class 2, class 3, class 4, or if it's actually outputting numbers on a spectrum that are just a value, like how hot is it going to be tomorrow? Not is it going to be hot, but how hot. So if it's outputting something on a spectrum, then that's regression. If it's outputting a class like, cat, dog, etc., then that is classification. So the dumb predictor, I was trying to lead you toward classification. If you do regression instead, that's fine, but it's harder to talk about what does it mean to have a good model. We get into that. We're going to get into that partly today, but that is the difference, regression and classification. Now, your homework for next week is to use a linear regressor. Now, the simple idea is just have a bunch of dots. Can you fit a straight line to those dots? There is a scikit-learn model you can use. If you want to be ambitious, you can do it yourself. You can code it yourself. And I will give extra credit points to things like that. But this course is mostly about learning how to use tools that exist and understanding what they do. You don't have to recode these things if you don't want to. So you're going to take your data, take you the same data you got for this project. And all the rest of the code can be the same if you want. But instead of your model that is a dumb prediction, use a linear regression. And you'll see things like in the example that they give you on scikit-learn, there's this line right here, where it looks like they just call fit straight up. Well, first of all, this thing, linear regression, open, close parentheses, is actually the creation of the object, just like I had you instantiate your object and then call predict. But here they instantiate the object and then they call fit. Now, the fit function is basically training. So what you'd be passing into it would be the training X and the training Y. X here is capitalized because it's a list of vectors, and typically, and Y here is not capitalized because it's a list of output numbers. Now, it turns out in this sample and in a lot of samples, it's really just one number that's predicting another number. Like, given the square footage of a house, can you guess the price? I would say those are obviously correlated. In one neighborhood, a house that's twice as big would definitely be worth more. It may not be worth twice as much, but it's definitely going to be worth more. So those numbers are correlated. That's a perfect example for using linear regression. So here is the fit. But down here is this predict method. And that's what you are using in your dumb predictor. Same thing here. Any questions? All right, let's jump in. This is going to come up a lot this semester. Who recognizes this equation? Everybody, good. The simple line equation. And we see this, of course, when we're doing a straight line, as you will be doing in your homework, but it comes up in a lot of other surprising places. Just keep it in mind, and I'll remind you of this when we see it again and again and again. Okay, let's talk about distance. What are some ways to calculate distance? Euclidean distance, yes. And what's another one? One that was mentioned 10 minutes ago by our colleague. Yes. That actually is Euclidean distance. Yes. There was another one though. That is another one. People talk about that, but he did not mention that one. What's the distance he mentioned? Called it something similarity. Yes. So cosine is another kind of distance. So out of these, which one of them do you think is Euclidean? What? Red? No. Yep, green. So green is Euclidean. And when you think about the Pythagorean theorem, right? A squared plus B squared equals C squared. So if you want to get C, it's the square root of A squared plus B squared. Which one of these is the Manhattan distance? You mentioned Manhattan, right? Red, you said? Yes, the blue one. Okay, so if the blue one is Manhattan distance, how does that compare with the red one and the yellow one? What? Same distance, yes. So Manhattan distance is interesting that it almost doesn't matter which way you go as long as you're somewhere in the main square, in the square region. You will always get the same Manhattan distance. So the Manhattan distance is not the real distance, but in some situations, like if you're in Manhattan, it's the distance that matters, right? We have another name for these distances. L1 and L2. L1 is the blue or Manhattan distance. And L2 is Euclidean. And what do you think that number refers to? Could I just switch them? The number 2 is specific to something. Yes, exactly. So L1, everything is raised to the exponent of 1. L2 is the square root of the sum of the squares. And this works no matter how many dimensions we have. If it's X, Y, Z, A, B, F, G, whatever. And the L2 norm of in a 3-dimensional space would be the square root of X squared plus Y squared plus Z squared. But guess what? There's also an L3 norm. What is a reason you might want to use an L3 norm? What's that? No, because we can do the L2 norm with 3 dimensions. We can do X squared plus Y squared plus Z squared. Square root. So you're getting there. For area instead, maybe. I'd use it if I want the function to feel it. When you're training something and you have a loss function, you're making it feel its status. Now, if you use the Manhattan distance and it's the error, it's say off by 5, what's going to feel at 5? But if you're using the L2 norm and it's off by 5, maybe partly in the X and partly in the Y, it's going to feel it more. Or maybe it's going to feel less, depending, because the Manhattan distance actually was more than the Euclidean, right? So maybe the Manhattan distance makes it feel it more. And the L3 norm is going to have different characteristics as well. So all of these can be used in different situations. As with everything, there is no single right answer. Now, this is what he talked about. He said similarity, not distance. Why the distinction? What's the difference between the similarity and the distance?
Similarities.
Yeah, it is very hard to compare distances. Similarities are easier to compare. But also they're kind of flipped. They're flipped versions from each other. Like if I'm vector and he's vector, as I get closer to him, the distance goes to where? 0. What's the similarity go to? 1. Now, if I'm as far away as I can get from him, then what is the similarity? 0. What is the distance? How far can you get away from something? Say infinite space, infinity, right? So, which sounds easier to deal with? Similarities. That's why we use cosine similarity to go from 0 to 1 instead of cosine distance. And if you have two things you compare over here, and they have a distance of, 23, and over here, they have a distance of 1,047. It's hard to know how to think about that. But over here, you got a similarity of 0.6, and here a similarity of 0.8, and we know how to deal with that. And you know how to deal with that instinctively, and that kind of means sometimes your models will train here. If you can intuitively make sense of input, oftentimes your models will be easier to train. Now, can you think of a scenario where no single distance metric would be perfect? There's the, go ahead. Curves. So curves. Yeah, like pretty awesome to find distance. Oh, curves. Yeah. Interesting. Yeah, I bet that it could work there. It could help there. Maybe L1 and L2. Well, there were a couple of big guys in machine learning, Chris Manning, Richard Socher, and Ty, I forget Ty's first name. They were working together on a paper, and they couldn't make it work with cosine distance. And they couldn't make it work with Euclidean. But there are times when both showed promise. So what they did, they took the L2 norm and they took the cosine distance or cosine similarity and fed them into a neural net to come up with the distance. Actually, I think they used the cosine distance, not similarity. And they came up with their own custom distance that was trained through the study. And you could throw in the L1 if you want. Well, as I have here. Assuming you have enough data and you train right. This is another way to do distance. Distance, in many ways, is subjective. What you're looking for is, are similar things close and the distance things different? You want anything that's dissimilar, you want to push them apart. Anything similar, you want to pull it together. That's what's going on in the guts. Okay, now we talked about this before. K nearest neighbors. Who can give me a quick recap in your own words? Don't think too hard. How are you?
Neighbors, in some cases, will have similar attributes, similar values of space. So the example we did was like your location in the US might correlate to somewhere decent.
Yep. And what K did we choose? 4. Yes. And part of the challenge is choosing the right K. Now, think about this situation. You know that this and this and this are close to this. Close means you're measuring distance, right? What if you have a whole bunch of features, not just 2 dimensions? How do you know that in every single feature, whether it's latitude, longitude, age, whatever it is, how do you know that you're calculating the right distance? See, this is another one of those questions you got to ask yourself. So if you're building a K nearest neighbors model, it's not just about choosing the optimum K. It's about choosing the optimum distance measurement across all your features. So what's interesting about this example is that for the brown one, we don't know if it's class A yellow or class B. I think that's from France or something, I don't know. It's class with an E at the end. Anyway, if we choose K equals 3, then obviously it's purple. But if we increase it to K equals 6, then obviously it's yellow. Keep those things in mind. Okay, now a few slides from Dr. De Palma. Okay, he likes to imagine a scenario where you're guessing a type of movie. So if we're going to classify movies, and let's say we just choose two features, the number of kicks and the number of kisses. It's pretty informative. You know, how many times someone gets kicked and how many times someone gets kissed in a movie. So let's choose just those two features. And we're going to train and we're going to read some data in. We're going to use Euclidean distance. We're going to choose a K. And then we're going to take a new movie that's not in our data set, try to predict what genre of movie it is. Okay. Has anybody seen at least one of these movies? Raise your hand if you've seen at least one of them. Wow, some people haven't even seen one. All right. So Blade Runner is actually my favorite out of all these. They talk about AI a lot, Blade Runner. It's actually really well done. But Blade Runner is the unknown. Started with 3 romances, which I have seen one version of Pride and Prejudice. I was forced to. It was okay. Jane Eyre, can't remember if I've seen it. Anna Karenina, maybe I've seen a preview. But Fist of Fury, great. Bruce Lee. Enter the Dragon, also Bruce Lee. And Outlaw Jesse Wales, Clint Eastwood, fantastic movie. A lot of kicks in those later movies. A lot of kisses in those early movies. Well, let's find out if K Nearest Neighbors can classify Blade Runner. Okay. We're going to compute Euclidean distance in our 2-feature vector space. Remember, just kicks and kisses. Euclidean distance from Blade Runner to Pride, Prejudice, Jane Eyre, Anna Karenina, Fist of Fury, Enter the Dragon, Outlaw Jesse Wales. Turns out it's really close to those first 3. Okay, let's let K equals 3. Why not? The 3 closest movies, Jane Eyre, Anna Karenina, Pride and Prejudice. You can see where this is going. What do you guys think about that prediction?
It's not a very good.
It's not a very good predictor. No, it's a bad model. What went wrong? What other features could we have pulled out? What would be the next feature? Number of fights. Number of fights. Maybe that would be better than kicks. This number of fights. Number of deaths, maybe. But there are a lot of romances, deaths. Maybe murders. Maybe that's it. A friend of mine used to classify really bad action movies with murders per minute. How many murders per minute are there? So this did not work. But the point is to give you an idea of why these things fail. Because most of the models you train in life will fail. Another thing to think about is maybe kicks and kisses should not be treated equally. Okay. Now, unless we're told otherwise, assume every feature is equally important, but maybe they aren't. Which term will make the greatest difference here? And we just give some example, but what we want is not features that go from 0 to infinity. 0 kicks to infinity. So it would be nice if everything could go in the same range, 0 to 1 is what I like. But some people like -1 to 1. There are other things you can choose. Now, when you normalize a feature like the number of kicks or the number of kisses, you're going to find that order is not violated. You're going to have everything in the same order that it was. But what changes? Something does change. The what? Yes. And the distance between you two, for instance, and you two, actually, let's make it right angle. So the distance between you two and you two, if we normalized it, we scaled it like we're doing here, it's going to change in what way? Like, will you just both be closer and go further? Go further, or what? What do you think? Is it going to change who's closer to you? Good. If you're at a right angle, you can change who's closer to you. All right, we're going to do another exercise where everyone stands up. So everyone stand up where you are and try to get relatively equidistant from each other. Okay, now I want you to look around and figure out who are the 5 closest people to you. Take mental notes. Now, without changing how far back you are in the room, I want you all to change where you are on this dimension. So everybody get shifted over toward this wall as close as you feel comfortable doing. All right. Now, look around. Is there anybody here for whom those 5 have changed? At least one person's changed. All right. That is what scaling can do. Any questions? You can all sit down. All right. We're moving on from K near standards to linear regression. So no more questions about that? Okay. Linear regression, simple machine learning model. You can even call it just ancient statistics. It's not really machine learning. It assumes a linear relationship. And assuming is actually a #1 thing that happens in machine learning. You assume some kind of underlying model, and you train that model on the data, assuming it will work. Now, if your data doesn't follow that model, then you're going to learn something that's not right. Now, it might still work sometimes, and you can be deceived into trusting it. So you got to be careful. But what's nice about linear regression is that typically you can graph it, plot it, and look at it. So let's say we have a whole bunch of dogs, right? Everybody can imagine where that line would be. We're all good at this. And I'm going to do a lot of repeating of things over the course of the semester and even today, partly because it helps you learn and partly because I forget sometimes when I've told you something. And I'm at that point in life when my daughter tells me, you told me that 10 times. So that's just going to happen. Be ready. How do I know for a fact that that's the best line? What makes it best? And yes, the hint is on the slide. The distance. But what kind of distance? What?
Shortest distance.
What kind of shortest distance? What? Square. Yes. Then minimizing the error squared. This is a really great case for the L2 norm. So you're going to have this error, and this error, and this error, this error. And you get that this error is defined as a perfectly vertical line from the thing to the function output. Your function, how do we describe this function? Y equals mx plus b. Very simple. So the output of y, whatever y is at this point, is where the red line is. So all of these, you want to minimize them, but you're not minimizing adding them up. It's just adding them up and taking the absolute value. What norm would that be? Anybody? Anybody? If you just added up the absolute value of all of these and minimized it, what norm would that be? L1, the Manhattan distance. Instead, we're going to minimize the sum of the squares, which functionally is the same as minimizing the square root of the sum of the squares, but why go through that extra last step if you don't have to? Somewhere along the lines, statisticians determined that minimizing the squares is better than minimizing the absolute value of the errors. Why? Because of like outliers. It punishes outliers more. Because you're punishing this one with the square of that distance, this with the square of that distance. There are times when statisticians found that in certain scenarios, not doing that it gives bad answers. There's a lot of depth into that field. You can read a lot about it a lot more. Now, if you were to use the L3 norm, what would happen? Yes. Now, when we say punished, what that means is that the line would adjust full toward the outliers. Of course, if you have outliers in both ways, then it balances. But we probably have more outliers down below than we do above, at least extreme outliers. Therefore, if we use the L3 norm, we would probably get something like this. And that would be listening too much to the outliers. L2 norm, there's a lot of statistics and theory and maybe 150 years of people using this probably. Here's another example. And intuitively, it just makes sense. You know what it's doing. The code in linear regressor makes this. This is what you'd be doing for your homework. You want to minimize the square of those errors. And we typically talk about the x as being the independent variable. The y is independent. So in my earlier example, with house sizes and prices, which goes where? Yep, and the price will be the dependent one. Now, how do we draw this if I was guessing the dependent variable price based on the square footage of the house and the height of the house? I have two variables now. Yeah. And then instead of a line, what is it? A plane. What if I add yet another? If I have three independent variables. it'll be another dimension. It'll be, instead of a plane, it's gonna be hyperplane is the word we use, yes. Now, it's basically a volume that goes on forever in every dimension, but it separates volumes of higher dimensionality. So you can think of it as a surface between them. Hyperplane is the way machine learning people tend to talk about it, because it's a perfect example that we can analogize onto this. You can see if you have three-dimensional space, you can cut it with a plane. If you have an n-dimensional space, you can cut it with an n-1 dimensional plane, hyperplanes. And a lot of the models that you guys will learn about, it's just about cutting the plane with a hyperplane, cutting the space with a hyperplane. Now let's get down and dirty. Here are some points. By the way, at the bottom here, this is a nice page. You can go to learn more about this. Here are a bunch of points. One of them's even doubled up. Two of them doubled up. Three of them, four of them, whatever. We're going to use these to fit a line. We're going to fit a line to these points. And maybe I took out the repeats. What's going on here? What is on that second line?
The errors, the squared errors.
Yes, squared errors. Now, if we want to, that's what we want to minimize right there, right? So we don't know what M and B are supposed to be. This M, this B, all we know is that we want them to be minimized, or we put them in set such that that gets minimized. What should we do next, mathematically? We're going to make another assumption. We're going to make an assumption that there is optimal M and B. That's proven. Don't worry about it. And we're also going to assume that if you have all possible M's and all possible B's, as you approach that optimal number, it's a smooth curve on the way to get it there. They also call this convex. We'll repeat that later in the semester to make more sense. So we can do this. There's no mystery here. What's our next step? Yes. We're going to take two different derivatives. We're going to assume that M and B can be treated independently. So we're going to take the partial derivative with respect to each. Why do we set it to 0? Yeah, minimize. And we're assuming that at that optimal point, it's a smooth curve that's convex, which means the derivative at that point with respect to B will be 0, and derivative with respect to M will be 0. It's kind of a meta space. So the space of our data is one thing. 1, 2, 2, 3, 4, 7, 5, 5. That's the space of the data. Now let's move over to the space of M's and B's. One dimension is M, one dimension is B. In that other space, space of our equation, at each point on the M and the B axis, in that two-dimensional space, you will get a value for line number 2. Let's say you just randomly choose an M and you randomly choose B. Then you plug them into line number 2. You will get the squared errors, right? Then you shift it just a little bit, get a new value. Better. Oh. Let's pretend this dimension is the dimension of B. Oh, it's a little better. It's a little better. It's a little better, it's a little better, it's a little better. Oh, it's a little worse. A little worse. So I come back here, it's fun. And I say, this, the best would be. Now, interestingly, it may not be the best now. So I'm going to just come in a little bit. It's a little better. A little better. A little better. A little worse. A little worse. Okay. So I've done the partial derivative with respect to B, and the partial derivative with respect to M. And right here is the optimal M and B for line number 2. Now, when I was going this way, finding that B, I could tell it was getting better that way. And then here, I could tell it was getting better this way. But when I was here, derivative is 0, right? And the derivative for M is 0 here, this part of the time. So this is the only point at which the derivative with respect to B and with M is both 0. So there's those two spaces we're dealing with, the space of the original points and the space of M and B. It's kind of confusing, isn't it? But it's just applied math you guys have all hated. This is what it all simplifies down to. Is this solvable? Give me your hand if you think it's not solvable. Give me your hand if you think it is solvable. Okay, why is it solvable? Yeah, how do you know?
I guess you could just assume that there's value in the worst case as check and on points. But in order to like derive the is the solve.
It's actually easier than that. 2 equations, 2 variables. You can utilize the second equation and replace the B in the first equation. B value of B. Exactly.
I'm just gonna say there's a system of equations that slows down to find out.
That's good. These are all right answers. So whenever you have 2 equations and 2 variables, then this is fully determined. What do you think it would mean if we had an overdetermined system? Or an underdetermined?
Overdetermined, we have more variables.
No, that's underdetermined. But you can imagine where it's going, right? More equations and variables would be overdetermined. If you have 10 equations, but only 2 variables, it's very overdetermined. And you might get lucky, maybe they actually do agree and there is an optimal M and B. Or maybe there's not, right? Could be this is not. Could be that you have 10 equations that are not able to agree with each other. That would be overdetermined. And you'll find that in machine learning a lot, and you just average things out. That's one way to think. An underdetermined one would be like if we had 1 variable. Now, if we had underdetermined would be not enough equations to resolve them all. So if we had 1 equation with 2 variables, that would be underdetermined. That means each of those variables would have multiple possible values that would fit. Like just the simple equation x equals y. How many answers are there? Infinite. 2 equals 2, but 100 also equals 100, right? Anyway, this is a fully determined system, so we know there is an optimal answer. And there it is. And as you can see, it fits the points really well. And that is everything for today. So let's talk about when you might want to use a linear model. You're going to be doing linear regression. How do you know when's the right time to use linear regression or some kind of classifier?
Classifiers can be used when we're talking about what we want a discrete answer and a regression on answer.
How about Zillow? What do you think Zillow is? What does Zillow do? Do you know? They're trying to predict one certain value. What is it? Yeah, property value, price, yeah. If you were to sell it right now, what would your house sell? Is that classification or regression? Regression. Now they use much more complex models than a linear model, but it's still this sense of regression. What other AI models have you guys done today? How about just today? Look like. Do we know? Is Google? Yes. So every time you do Google search, a lot of AI behind the scenes. When you do a Google search, is that more like classification or more like regression? All right, who said regression? Okay, why is it like regression? Because it's just a percentage of and maybe it's using cosine similarity between your query and the possible results, right? But it can also be a classification, right? Why? I'm just thinking it's like hard title, it's like strings, classifying strings, not numbers. I like this thing where so I'm sure we got classifications. Determine type of regression. So if you look up something, what's something similar to what you're looking at? What's the type of regression? About basketball games and not just What might Google use to narrow down what it thinks you're asking? If you just say basketball games, it's not going to show you basketball games over in Australia. Location is a big part of it. Time, another one. Yeah, what basketball games are coming out? That. What else might you use? Past searches. Past searches, yes. It probably knows you're an Gonzaga student. So it might paper results have to do with Gonzaga basketball. Now, it might work differently if you go to a school that has a terrible basketball team. Because maybe no one else is searching for their results anyway. So they're like, oh, you must have been Gonzaga. What other kind of AI might you guys have interacted with today? What's that? Yes. When you open your phone, right? How does that work? What does it do? What do you guys think? Yeah, how does facial recognition work?
It takes whatever's in front of it, tries to classify your face or
Yeah.
something not your face.
Yeah, so it's a classifier, right? Face, your face or not your face. Obviously, identical twins are often able to open each other's phones. kind of look like. It's not perfect yet. How can you take a regressor and turn it into a classifier? Under the covers, that facial recognition thing might actually be a regressor, saying how similar the face sees to one record. How do you turn that into classification? Threshold. Now, it would be another fun little extra credit thing, although you don't have to do it this week. You will do it in another week where you take what is basically a regressor and find a threshold and use that for classification. Have any of you guys seen the show Silicon Valley? What was early on the very stupid classifier they built? Remember? They classified images. They take a picture of something.
So like a food one, like this
Yeah.
is a hot dog. This, hot dog.
Yeah. Yeah. So this guy is all excited about it. He made it. He brings it to someone and says, "Hey, I got this hot dog classifier." And the guy didn't really quite hear him or understand. He says, "Point your camera at this hot dog." And he does. He's picture the hot dog. Say, "This is a hot dog." Yes, it's awesome. It's accurate. Then he points it at pizza, and he expects to say this is pizza, but all it says is, "This is not a hot dog." See, it's perfectly accurate. Points it at his friend. It's not a hot dog. At his car, it's not a hot dog. Yes, it was accurate, but no, it wasn't useful. How could you make that thing useful without fundamentally changing the technology? But yes, and there is actually a psychic learning model that will do exactly that. And what you do is you find features for a whole bunch of things, plot them in a space, and you train one model to look at all those features and say, this is a hot dog, not a hot dog. And let's say you got some data points in your space. And you have in here maybe hot dogs. You got pizza. You got apples. And say lettuce. So you train a model that's, lettuce or not lettuce. And you train another model, hot dog, not hot dog. Pizza, not pizza. And if we're doing just straight lines, this last model is not going to be very accurate. Apples, not apples. If you were to combine these, how do you do that? To one model that can recognize all four things. It's called a one versus rest model. Multi-class, but one versus rest. How do you take the output of all four? Fine. Guesses. Is each of these four models, is it just a classifier? It is. It's just going to give you a 1 or a 0, right? Let's say I give you a new point, and this new point happens to be here. What is it? It's lettuce, but it's also an apple? Clark,
Well, if you're using vegetables, then you go whichever.
that's it, lays the most claim. How do you measure that?
Which one is closest to
All we have is this, we have a hyperplane dividing each.
it's farthest area.
Farthest from the border, right? Yeah, that's one way you can do it. And in this case, it looks like it's an apple. Because it's barely in lettuce, but it's a little bit more inside apple. So you could say it's an apple. The intuition is sinking in, right, guys? Any more thoughts or questions? All right. Go for it, guys. Thank you very much.